The concept of liquid-shielded domes represents a frontier in protective infrastructure. A continuous liquid layer offers significant protection against a diverse range of external hazards. However, designs incorporating such a layer are exceedingly rare due to the substantial engineering challenges involved in their realization. The protection provided by a liquid layer is multifaceted. For fragmentation and ballistics, the liquid dissipates kinetic energy, effectively slowing and dispersing projectiles. This mechanism reduces the impact force on the underlying structure. Against blast and overpressure events, the liquid cushions the shock. It transmits pressure as hydrostatic waves, distributing the load over a larger area and mitigating localized stress concentrations. This acts as a dynamic buffer. In thermal and flame scenarios, the liquid acts as a high-capacity heat sink. Its specific heat capacity delays heat transfer to the protected interior, offering crucial time for response or evacuation. This thermal buffering is a key advantage. For ionizing radiation and neutrons, liquids like water are effective shields. They are particularly good for attenuating neutrons and offer moderate effectiveness against gamma rays, depending on thickness and composition. This makes them valuable in nuclear applications. Regarding acoustic and vibration damping, liquids can absorb certain energy frequencies. However, careful engineering is required to prevent the liquid itself from transmitting unwanted vibrations or acoustic energy. This necessitates specific design considerations. In cases of buoyancy or direct impact, the liquid absorbs kinetic energy by converting it into fluid motion. This fluid dynamic response distributes the impact force, reducing peak stresses on the structural elements. The effectiveness of all these protective mechanisms scales directly with the liquid layer's thickness. The rarity of liquid-shielded domes stems from profound engineering challenges. The sheer weight of the liquid creates enormous dead loads, imposing significant demands on foundations and structural integrity. This necessitates robust and often oversized support systems. Hydrostatic pressure is another critical factor, increasing linearly with depth. This requires exceptionally robust containment structures and sophisticated pressure balancing systems to prevent structural failure or leaks. Seals and penetrations are particularly vulnerable points. Containment and the risk of leaks are paramount concerns. Every seal, pipe, or access penetration represents a potential leak path, demanding redundant sealing technologies and continuous monitoring. The consequences of a large-scale leak can be catastrophic. Environmental factors introduce further complexity. Freezing temperatures necessitate heating or antifreeze solutions, while evaporation requires replenishment. Biological growth, such as algae or bacteria, can foul the liquid and require continuous treatment. Maintenance and repair. Within such systems are inherently difficult and disruptive. Accessing the liquid layer or its containment structure for repairs can be complex, often requiring partial or complete drainage. This impacts operational continuity. Dynamic loads. Transmission is a significant concern. Liquids can transmit shock waves, leading to phenomena like water hammer or sloshing, which can induce secondary stresses on the structure. Active damping mechanisms may be required. Ultimately, the cost and complexity of liquid-shielded domes are substantially higher than typical solid armor options. The specialized materials, construction techniques, and ongoing operational requirements contribute to this increased expense. Several candidate liquids exist, each with trade-offs. Fresh water is cheap, non-toxic, and has good heat capacity, but it freezes and promotes biological growth. These issues require active management. Salt or brine solutions offer a lower freezing point, but they are corrosive to many common construction materials. This necessitates specialized, corrosion-resistant containment and piping. Glycols provide freeze protection, but ethylene glycol is toxic, and propylene glycol, while safer, is more costly. Their use requires careful consideration of environmental impact and cost-benefit analysis. Silicone oils or synthetic hydrocarbon fluids offer a wide operational temperature range. However, they are expensive and generally possess lower heat capacities compared to water. limiting their thermal buffering capability. Selection criteria for the liquid include heat capacity, freezing point, density, and chemical stability. Toxicity and cost are also critical factors, influencing both environmental safety and project viability. Practical construction approaches often involve a double-shell dome with an outer liquid basin. Here, the inner habitable shell is structurally independent from the outer liquid tank, isolating the living space from the liquid's weight and dynamics. Alternatively, a membrane containment system can be bonded to a rigid outer dome. This corrosion-resistant membrane acts as the primary liquid barrier, protecting the structural shell from direct contact with the fluid. Layered defense strategies combine thinner liquid films with solid sacrificial layers. This hybrid approach leverages the benefits of both liquid and solid protection, optimizing for specific threat profiles. Active damping and slosh control are crucial for managing dynamic liquid behavior. Baffles or partitions within the liquid layer can mitigate sloshing, while active systems can counteract induced vibrations. HVAC, filtration, and chemistry control are essential for maintaining fluid properties. Continuous treatment prevents freezing, evaporation, and biological contamination, ensuring the liquid's long-term effectiveness. Simple engineering numbers highlight the scale of these challenges. Water's density of 1,000 kilograms per cubic meter creates immense mass, directly translating to significant structural loads. Hydrostatic pressure increases linearly with depth, calculated as pressure equals density times gravitational acceleration times height, pH/rg. This dictates the strength requirements for containment. Water's high specific heat capacity provides excellent thermal buffering, delaying temperature changes within the protected volume. This property is invaluable for thermal protection. The freeze risk necessitates heating or antifreeze systems, which add to the energy budget and operational complexity. These systems must be robust and redundant. Use cases for liquid-shielded domes include nuclear shielding, industrial facilities, experimental environments, and critical military or civilian infrastructure. Their specialized protection justifies the complexity in these high-stakes applications. Practical recommendations include defining the precise threat spectrum and calculating all associated loads. Exploring hybrid designs that combine liquid and solid elements can optimize performance and cost. Consulting specialized engineers and prototyping small-scale systems are crucial steps before full-scale implementation. Closed-loop life support systems are essential for sustainability within a liquid-shielded dome. These systems manage waste, water, air, energy, and resources through continuous recycling. They must be modular, redundant, and designed for uninterrupted operation. Solid waste recycling and processing begin with meticulous source separation. Organics, recyclables, plastics, hazardous materials, and bulky waste must be segregated at the point of generation. This maximizes recovery efficiency. Organics management typically involves aerobic composting or anaerobic digestion. Composting produces nutrient-rich soil amendments, while anaerobic digestion generates biogas for energy and digestate for fertilizer. Residuals that cannot be recycled or composted may undergo thermal conversion. This process reduces volume and can recover energy, but requires advanced emissions control to prevent environmental contamination. Wastewater management involves collection, treatment, and reuse. Plumbing separation is critical, treating black water from toilets and gray water from sinks and showers separately due to differing contamination levels. Black water treatment typically includes solids removal, followed by anaerobic digestion. Membrane bioreactors, MBR, or aerobic filters further purify the water, removing pathogens and dissolved organics. Gray water treatment is less intensive, often involving filtration and biological filters. Advanced oxidation processes or UV disinfection ensure high-quality water suitable for various reuse applications. Water reuse follows a hierarchy, starting with non-potable uses like irrigation or toilet flushing. Processed water for industrial applications and, ultimately, potable reuse for drinking are progressively higher tiers. Nutrient recovery from wastewater is vital for closed-loop systems. Methods like struvite precipitation or ion exchange can extract phosphorus and nitrogen, converting them into valuable fertilizers. Air induction, filtration, and environmental control are paramount. A robust ventilation strategy employs mechanical ventilation with heat recovery ventilators, HRVs, or energy recovery ventilators, ERVs, and demand-controlled systems. Filtration stages include pre-filters for large particulates, HEPA filters for fine particles and pathogens, UVGI for microbial inactivation, and gas phase adsorption for volatile organic compounds, VOCs, and odors. Pressure and zoning strategies maintain air quality and prevent contaminant spread. Positive pressure in core habitable areas, with pressure gradients towards hazardous zones, controls airflow direction. Carbon dioxide, CO2, and chemical control are managed through closed-loop systems. CO2 scrubbers or biological air purifiers maintain safe levels, while chemical scrubbers remove other airborne contaminants. Redundancy and isolation are built into air handling units, AHUs. Multiple AHUs, bypass ducts, and emergency backup systems ensure continuous operation and allow for isolation during maintenance or contamination events. Interfaces between the living sphere and the water walls require careful design. Contamination control is achieved through a chemically and biologically controlled water layer and double-sealed penetrations. Thermal exchange utilizes the water layer as a massive heat sink or source. Heat exchangers and glycol circuits stabilize the interior temperature, leveraging the liquid's thermal buffering capacity. Leak detection and mitigation systems are critical. A sensor mesh monitors for leaks, while automated pumps and isolation valves can quickly contain and address any breaches. Biosecurity measures for the water layer include UV and chemical dosing, continuous circulation, and separate tanks for potable water versus structural water. This prevents cross-contamination. Slosh and structural coupling must be managed. Baffles, compartments, and dampers within the liquid layer mitigate dynamic forces, preventing them from transferring to the inner structure. Energy, heat recovery, and resource loops are integrated. Biogas from anaerobic digestion, thermal recovery from exhaust air, and heat pumps contribute to energy efficiency. Electricity is supplied by a microgrid, incorporating renewables, combined heat and power, CHP systems, and battery storage for resilience. This ensures energy independence. Nutrient and material loops close the resource cycle. Compost and digestate return nutrients to agriculture, recovered materials are reused, and treated water is continuously recycled. Maintenance, operations, and safety culture are foundational. Redundancy, N+1 for critical systems, and physical segregation of infrastructure corridors enhance reliability and safety. Accessibility and modular replacement are key design principles. Systems are built on skids or in containerized modules, allowing for easy access, repair, or replacement without major disruption. Emergency protocols include quarantine rooms, clearly marked evacuation routes, and integrated firefighting systems. These are essential for occupant safety and rapid response to incidents. A practical summary for life support prioritizes robust source separation and modular treatment. This allows for efficient processing and scalability. Air systems must be designed for advanced filtration, effective zoning, and inherent redundancy. This ensures a safe and controlled internal atmosphere. The water wall can serve as a thermal buffer or emergency water source, but it must remain isolated from potable systems. This prevents contamination risks. Recovering energy and nutrients locally minimizes external dependencies and enhances sustainability. This closes critical resource loops. Finally, building layered defenses and ensuring easy access for maintenance are paramount. These principles underpin the long-term viability and safety of any liquid-shielded dome with closed-loop life support.